Alright guys, hey, it's me, Reclaimer Sean again, and today I'm here to bring you the second video of 4 of the Making Xbox 360 RTE Tools installment series. In theory, I might make more videos for specific examples in the future, but for now, I'm going to start you out sort of with the basics, and the facts that this is the basics should show that there's a lot you're about to learn. So, Part 2 concerns the PowerPC assembler language, also known as ASM or PPC. You will need the following. All the previous things from video number 1. You will need a modded console of XDK build installed and shadow booted to RG loader or an XDK shadow booted to RG loader. Either you shadow boot to RG loader or you patch every game.xex to be dev compatible and hope the game boots. In my experience, works 50% of the time, doesn't work the other 50% of the time. I just shadow boot to RG loader, makes things much easier. Regardless, you're still going to need XDK build or an XDK. XDK build being used for modded consoles, XDK being a real console that Microsoft made. You'll need that your console connected to your computer via Ethernet or PIX. If you're using, there's a PIX port on older XDKs, and you might need to connect to that. But my XDK is just using Ethernet, and that works fine. You'll need a program called PyASMH3 downloaded and installed. This helps us to turn custom instructions that we write into bytecode that can be pasted into the memory of the game. And you'll need full installation of the Xbox 360 software development kit, including Xbox 360 Neighborhood, Visual Studio 2010, XB Watson, etc. These are official files from Microsoft. I will not be providing them. Okay. What is PowerPC? So I'm actually going to split this video up into 2 videos because if I don't, it's going to take forever and people are going to be overwhelmed after the first one. So it is what it is. So what is PowerPC? PowerPC is the programming language the Xbox 360's processor uses. By learning the basics of this programming language, we can more effectively make cheat codes, especially ones involving dynamic addresses. Unfortunately, most addresses are dynamic addresses, so you're going to need all this information to do even anything, to tell you the truth. PowerPC has these things called instructions, which are one single line of code that does something. It also has functions, which is a bunch of instructions together whose job is to accomplish a purpose. For example, one instruction may store how much ammo you have left in your gun to memory, while a function of several instructions first calculates how much ammo you have left and then stores the remainder to the memory. PowerPC lives inside the default.xex of the game file. This is basically the game's executable file. You can typically find the default.xex in the memory range OX 8200 and up, and this is generally only on one memory range at a time. By using PowerPC, we can not only write to dynamic addresses, but we can change to how the game works itself. So to understand instructions, you're going to have to understand registers. Registers are basically boxes that hold things to be used later. Registers can hold values by themselves, the value of an address, or an address itself. The PowerPC programming language will take things to and from registers to perform operations to in-game memory. The idea is your registers are basically things you can throw things in and out of to get something done. We get 31 general purpose registers, GPRs, to work with, including R0 and R2 through R31. We get 32 floating point registers, also known as FPRs, including FR0 to FR31. There are special registers. Of concern to us include the programming counter / the instruction address register, also known as PC / IAR. I'm going to call it PC. Visual Studio calls it IAR. I'm going to call it PC for the rest of this video. The link register is known as LR, and the stack register, the stack pointer, is known as SP or as R1, which is why we only have 31 GPRs. PC contains the address for the current line of code being ran. LR contains the address of the last instruction executed before a function was left plus OX4, allowing for the game to move from function to function and instruction to instruction as necessary. SP contains the location of a special space in memory that can be used to store things for later. More on that later. The first instruction is the store instruction. So you'll notice the general format here. It's RA, DRD, where RD plus D is the register we're storing things to, is the place we're storing things to in memory, so the memory address. RA is the value that we're storing, and the ST and the way the store function is written depends entirely on how much data we're writing to memory. If we're just storing a byte, you use STB. If you're just storing 2 bytes or a half word, you use STH. If you're storing 4 bytes or a word, you use STW. If you're storing a floating point or a floating single, as it might be called, you're using STFS. Basically, what this does is this takes a register and sets an address in memory equal to that register. So let's assume R2 equals OXF for a minute, D equals OX4, and R3 equals 4C214. So this is what this is going to do. First off, it's going to add these two registers to give us 4C218. Then it's going to write the value of R2 or OXF into that memory address. So now, if you look at Peek Poker, after this this instruction executes, address 4C218 would be OXF. An example, you'll often be writing to these because this will be things that are like storing your ammo value to memory, your memory value, your health value to memory, etc. Most of what you're going to be writing to is stores at the end of the day. Then there's loads. This has the same format as STW, sort of. So first off, this is going to take the memory found in D plus RA and store it to RD. So basically, this copies a value from memory into the register of your choice. Once again, same formatting. Load byte, load half word, load floating single. If you're wondering what the Z is, it's 0, so load byte 0. It just sets whatever this value was to 0 before it pops the value of your choice in. So let's assume for a minute that we're using the instruction LBZ R2 OX4 R3. R2 is going to contain any random value. Doesn't matter because R2 is not going to exist anymore, and it's going to be replaced with what we get. Let's say OX4 is D, and R3 is 4C214, and the value contained by 4C218 is OX9. So OX4 plus 4C214 equals 4C218. So this is going to take the value contained by this memory address, which is OX9, and store it in R2. R2 now equals OX9, the same thing that it did in the memory And the previous value in R2 is gone now. You're not going to be able to find it. A reason that the game might do this, maybe it loads the ammo that you had before you fired your gun to know what to adjust your gun to after it fires. Or maybe it's comparing something to see, okay, does this player have enough money to buy this item? If they do, let them. If they don't, don't. So those are some uses for that. There's load immediate, LI, RD, OX, 4 question marks. Lets you set a register to any value of your choice from 0 to FFFF. Lets you set a register to any 1 or 2 byte value of your choice. Assume R2 is any number before this runs. After this runs, it will be the number that you set it to, erasing the previous value. Now there's load immediate shifted, and or immediate. To simplify this a lot more than what it's really doing, basically these are two instructions used together to make a register a 4-byte value of your choice. So LIS, load immediate shifted, RA, YYYY, this sets register A to have the first 16 values be whatever you set, and then ORI, RA, ZZZZ sets the right half of RA to be the value of your choice. So let's assume we execute, because these are usually used one after the other. Let's assume these are both running. The first instruction, LAS R2 OX7FFF, runs. The previous value of R2 is discarded, and the current value of R2 is OX7FFF. That gets copied into the first 4 characters here. Then, this next OR-E instruction runs, loading the last FFFF, the other 4 values of your choice, into the rightmost portion of the memory. Now you've loaded a 32-bit value of your choice into memory, or 4 bytes, whatever you want to call it. So this one's kind of self-explanatory. The sub instructions, basically this subtracts RA from RB, stores the result in RD. Same with sub I or sub immediate, subtracts whatever's in the immediate, the pound symbol, which is usually a value from 0 to FFFF, and then it stores that result in RD. When this function executes, only RD is changed. RA and RB, as well as pound, are left the same. So assume for a minute that R2 is any random value, R3 is 4, and R4 is 3. So when sub R2, R3, R4 executes, first off it does R3 minus R4. So in this case, 4 minus 3 equals 1. Okay, the result of that is 1. Store the value OX1 into R2. Previous value is discarded. R3 and R4 are unaffected. Kind of the same thing with sub I. I don't know why I made the typo here, but sub I is right there. There's an I. Pretend the I is there. Sub I, R2, R3, pound OX3. Assuming R3 is OX4, pound is OX3, R2 is now equal to OX1 with the previous value discarded, R3 is unaffected. Add is effectively the same thing, but with adding instead of subtracting. So let's say here R2 is any random value, R3 is 4, R4 is 3. 4 plus 3 equals 7. Store OX7 in R2. Don't affect R3 or R4. Another typo. Cool, I'll fix that. Okay, so let's say that maybe to make sense of all that garbage I just told you, let's put load, sub, and store together. This might be a function that subtracts bullets from your ammo. Assume R2 is your current ammo in game, and R3 plus D is the address of your ammo. So basically what this is going to do, this instruction loads the current value stored by your address in ammo to R2. So load your ammo into R2. Let's say you shot 1 bullet, or every time you press the trigger, it shoots 1 bullet. It's going to subtract 1 from R2. And then now that your new value of R2 is R2 minus 1, store that right back to the ammo address. And now that's what your ammo equals in game. So you can also use load, immediate, and store together to give a custom value of what you want the memory to be instead of having to calculate it. Let's say you have ammo and you're wanting to make the ammo 255. And let's say we're using R2 as the register. R3 plus D is the address of ammo once again. So this sets R2 to OXF, so 255 bullets. Now store 255 bullets to the ammo address. Move register, very simple little instruction. Uh, Moves the contents of RB into RA. Assume R2 is any value and R3 is 0x7. So execute MR, R2, R3. R2 now equals R3. R3 was 7. R2 is now 0x7. R3 is unaffected. Nop. It literally does nothing. That's the point. So what you do is you replace a store instruction with something like a nop, and basically what happens is the subtracted ammo never gets loaded to memory, and as a result the value is freezed in place. This kind of lets you make things like infinite ammo or infinite life, stuff like that. Okay, things get a little harder from here. The compare and the branch instructions together, which I'll go over branch after this, make if-then functions. Basically, if your value is equal to this, then do something. Otherwise, do something else. How does it work? So let's say compare word RA to RB. It subtracts RA from RB, doesn't store the result, but it stores the comparison. So it would store, okay, was RA equal to RB? Was it less than RB? Was it greater than RB? Was it not equal to RB? That's kind of what happens. So compare does the comparison to see if something's equal, not equal, etc. And then branch does the final action. So in a way, the compare is the if, and the branch is the then of the if-then statement. So let's give an example of compare being used. Okay, assume at the time that the compare instruction was used, R2 is equal to 0x3 and R3 is equal to 0x5. Once this instruction executes, the game is going to remember that R2 is not equal to R3, and it's going to remember that R2 was less than R3. So let's give another example. Let's say R2 is actually equal to R3. Not equal to R3. Let's say R2 is actually equal to 3. Compare R2 to 3. If R2 is 3, which it was, and that is 3, then look, R2 equals 3. So it stores the was equal to memory, basically. There's a lot of typos in this. If I do release these PowerPoints, they will be corrected without the typos. These are the branches. A B to a target address, or a branch to a target address, branches to the target address no matter what the condition is. So that compare instruction could have ran previously, doesn't matter. It's going to go to that place regardless. Where it does start to matter is with the branches with conditions on the end. So BLE, branches of less than or equal to, BLT, branches of less than, BEQ, branches of equal to, BGE, branches if greater than or equal to, BGT, branches if greater than, B and E, branches if not equal to. So let's kind of give an example of this. As I said, it's basically an if-then function. If the value in R3 is equal to 0x4, then execute the code starting at target address. Otherwise, execute the next line of code and don't execute code at the target address. So you remember how I said the PC register was the current line of code being executed? The branch instruction works by changing PC to equal the instruction that you want ran next. So here's an example of both together. Let's say we're comparing R3 to 4. If R3 equals to 4, branch to the target address and start executing code there. If R3 equals 4, set PC to target address and execute code. Otherwise, if R3 was not equal to 0x4, then nothing happens. So that might be an example of something. Whereas if this had happened, it would jump away from the NOP and then go into something else and then maybe come back later if something was there to tell it to cut back. Speaking of coming back, BLR is another instruction. BLR branches to the link register. The link register kind of lets you store where your last place was in memory, that your last function in memory that was being executed, so you can come back to it later after some other operations are done. So let's give an example. Let's say the current program counter is 821C and the link register is 8228. Okay, so here's what's going to happen. PC is at 821C, so we execute the instruction here. Execute that instruction, execute that one, and then we hit a branch to 8240. So then we pop over to 8240, which is the target address right here. Execute, execute. Oh, LR is equal to 8228. Now that this hits, BLR takes PC and changes and makes it equal to LR. Since PC is now 28, we pop back over to 28 and execute the instruction here. That's kind of how the flow of things is going to work. Okay, we have finished the learning portion of this video, and in the next video we are going to go on to the practical portion. Stay tuned for the third video. Thank you guys. Take care.